All right, so what I want to do next is talk about some vector isomorphism examples. Okay, so vector isomorphisms. So what I want to do is I want to think about, we can think about a few things here. Let's say I want to take a vector space T, and what I'm going to do is I'm going to map, say, R4 into the vector space of M22. So I'm going to take the set of 4 tuples, so the set of ordered, 4 tuples. So remember R4, I don't have a nicer way to say that, just the set of x, y, z, w, where x, y, z, and w are in R. So this is R4. You can think of this kind of as 4-dimensional space if you want to think about it that way. And M22 is the set of 2 by 2 matrices with real entries, so A, B, C, D, where A, B, C, and D, again, are real entries. And so you can already see that these are similar in that there's 4 elements in either of these. It turns out that these are isomorphic because what's the dimension of R4? Well, the dimension of R4 is 4, and that's also the dimension of M22, because the dimension of so the set of M by N matrices has dimension M times N. Okay, so in our case that's 2 times 2, so that would be 4-dimensional. And so what this means is that we can find a isomorphism between these 2 vector spaces, R4 and M22. So for example, if I were to take T going from R4 to M22, what we could do is I could take T, so that could be X, Y, Z, W, and there's lots of isomorphisms. All I really need is for there to be at least one isomorphism for these 2 vector spaces to be isomorphic, but it turns out that there's lots. There's infinitely many. We could do this in a straightforward, boring way, X, Y, Z, W, right? That would be one way that we could map this function onto the others. So we can map R4 onto M22. Let's see. I could also have something a little bit more interesting. So again, this is an isomorphism. I could have T going from M44 to M22 be given by, say, so let's see, we have X, Y, Z, W. Could be given by, let's see, what do we think? So it could be given by, say, 4x plus y, z minus w, z plus w, and what else? So 4x plus y, z minus w, let's just say y. Okay, and it turns out that that would again be, this one's a little bit harder to see, it's a little bit more interesting, but it turns out that this will be an isomorphism. Okay, the only way to get all of these quantities equal to 0 at the same time is, so it's probably easiest to check that the kernel of T is just the 0 vector. Here, this is the 0 vector in R4. So it's the vector 0, 0, 0, 0. And if the kernel is just that set, then we know that it's 1 to 1. So this is worth writing down. So this implies that T is 1 to 1. And since R4 and M22 have the same dimension, that implies that T is also onto, and therefore an isomorphism. Okay, so there's another, again, isomorphism between the two vector spaces. Let's do one that's a little bit more interesting. Let's look at T mapping the set of 2 by 2 matrices to the set P3. Remember, P3 is the set of polynomials of degree at most 3. So what we could do here is I could take, as our input, I can take the matrix A, B, C, D. And then as our output, there's lots of different options to make this an isomorphism. You could take, probably the easiest one would be something like ax cubed plus bx squared plus cx plus d. Right, that would be how you would go from a matrix to a polynomial. So I think it's actually worthwhile in this case to just actually go through and see what that would look like. So if I were to take and input the vector 1, 4, 2, 3, our output would be the polynomial 1x cubed plus 4x squared plus 2x plus 3. Right? That's what this is telling us to do. Right? That's how we get a polynomial from a matrix. And again, you can check that the only way to get, this one's perfectly straightforward, but the only way that you can get 0, and by 0 I mean the 0 vector in P3, is if all of these inputs are 0. If any of these inputs are non-zero, then you don't get the 0 vector. In other words, we know that the kernel of T is just the 0 vector. In this case, it's the 0 vector in M22. And that tells us that T is 1 to 1. And because M22 and P3 are both 4-dimensional, right? Remember that for P3, we have a basis of 1x, x squared, x cubed. So it's a 4-dimensional vector space. And so because they have the same dimension, this means that T is onto and hence an isomorphism, since it's 1 to 1 and onto. Okay, so there's some examples of vector spaces. Just a few other things to talk about. And really, I just want to go over this one idea. So let's let T be a vector. So T is going to be a linear transformation between the vector space R3 and the set of polynomials P3. And what I want to say is come up with whatever function you want here. I don't care what it is. Just come up with whatever function you want. This linear transformation can never be an isomorphism. Okay, it just can't ever be an isomorphism. You can never have an isomorphism between two vector spaces with different dimensions. Right? R3 is a 3-dimensional vector space. P3 is a 4-dimensional vector space, right? Because it has 4 basis vectors. So that means that this can never be a vector isomorphism.